graphics characters that are available on the Commodore's keyboard. Now we've used the symbols on the tops of the keys, but all the letter keys and some of the punctuation keys also have these pairs of square symbols on the front face. And we type these when we want to type graphics characters. The Commodore Shift and the ordinary Shift key on the left-hand side of the keyboard are the keys that allow us to access these extra graphics characters. If we type a Z by itself, we simply get a capital letter Z. But if we hold down the Shift key while we type Z, we get a diamond instead of a Z. Similarly, when we hold down the Commodore key and press Z, we get that little bottom left-hand corner symbol. Now, if you look at the range of symbols that are available, you'll see that we can put together some quite complicated shapes. For example, a series of hearts using the Shift key and S, a series of top right-hand corners using the Commodore key and the S key together. Now, I've created a little maze shape using some of these graphic symbols. Here I've used curves instead of right angles, but in exactly the same way, this maze is made up of characters on the keyboard. These short curved shapes come from the characters U, I, J, and K. U has a top left, I a top right, J and K the two bottom quadrants of a curve. So by printing them one beside each other, or one below the next one, on the screen like this, I can get a continuous line. I've used two other characters on this screen, a horizontal line here, and a vertical line. The horizontal line comes from the C character, and the vertical line from the B. Here's the coding that produces that maze. A pile of print statements. Each is printing a string, quotation mark at the beginning, and a quotation mark at the end. And in order to type all the characters that are in the string, I've used the Shift key, and those keys I described to you on the keyboard a moment ago. The nice thing about this is that as we enter all our print statements, we can actually see the shape of the maze being built up. What's more, we can use the editing facilities, having listed the program, to say, I'd like a line to go to a different place, or something else to be a different shape. We can edit that one line, make the change, and see immediately the effect that change is going to have. I'll show you that by making this curve to the right. I use the up arrow to take my cursor to line 1060. I move right across that line until I'm positioned on the character that I want to change. Now, holding down the Shift key and using the U, you can see I've over-typed that vertical line with a curved line. As soon as I press return, that new version of line 1060 has been put into my program. You'll see that it has taken effect if we clear the screen and list it again. There we are. Line 1060 has now got a curved top instead of the straight top that the line on the other side has. I should make a small comment about the first two lines that you see in this coding. Line 1010 prints two of these funny looking symbols. The heart is the clear screen symbol, and that reversed left-pointing arrow means print in blue. So the whole of this maze is going to be printed in blue. Poke 53,281.15 turns the background to the screen this light grey colour. And the blue and the grey give us quite good clarity. Line 1000 is a line starting rem. This stands for remark. And what I've put after the word rem isn't basic at all. It's just English. Because after a remark, I can type anything I like into my program. The basic interpreter won't look at whatever I've typed there. So I can put little comments to myself, little reminders about what each part of the program does. As the programs get longer and longer, it becomes more important to put remarks into the program so that you or somebody else can easily see just what the program does. So we can use the print statement and the graphics characters to compose almost any shape we like on the screen. Remember the Shift key to get the graphics character on the right, and the Commodore key to get the one on the left. Now before we leave this basic maze, there's one other statement that I need to show you that's part of this coding. And you see it here at the bottom of the screen. I've given it a number of 1999, and it's a return statement. This is because this is going to be part of a much bigger program. That's one activity within the program, printing the maze. Within the program, there are going to be various other activities. So we need to divide the program down into small sections. If I show you the beginning of the program, you'll see what I mean. This list statement will list all the lines from the beginning up to line 1040. There's line 1000. That's the start of the routine you just saw to print the maze. Well, I've got two lines before it. Line 999 is the end of the program. So when we come to this line, we'll stop. Line 10 says go sub 1000. Now go sub stands for go to subroutine. And this is a very convenient statement when we want to divide our program up into separate sections, whether they're going to be executed one after the other, or whether one of them is going to be executed many times. The effect of this statement is to go to line 1000. And that's the first line of the print the maze routine. Now we'll execute all the statements till we've printed the complete maze. But if you remember, at the end of that coding was a return statement. Let me list it for you now. When we come to line 1999 and execute the return statement, we come back to the statement following that go sub. So all the coding from 1000 to 1999 is one separate section of coding, and we can execute all the statements in that coding by just saying go sub 1000. Very useful statement, go sub. Passes control to the line number you specify, and will continue to execute statements until a return statement is found. And when return is found, we come back. In this case, we simply come to this statement, end, and so the program stops. But as this program gets more and more complicated, you'll find that the beginning of our program consists of a series of go subs, and then the rest of the program consists of a series of routines, each finishing with a return statement. We can set up a maze, therefore, using whatever characters we like, and we can make that into a little subroutine by ensuring that we've got a return statement at the end of it. Now we're going to take a short break in a moment, and we'll save onto the soundtrack of this video cassette the maze that I've been showing you. What I'd like you to do is to copy it into your own computer and experiment using the graphics characters to make changes to it, to change the shape of it, or of course to change the color, because even when we're printing the graphics characters, we can still include color control codes in the strings of characters we're printing, as you can see here. Here's a slightly modified version, and you can see that the center section is printed in green. If I clear the screen and then list this slightly different version of the program, you'll see how I've achieved that. Clear, L-I-S-T. There are my 6 color control codes. You remember the left pointing arrow in reverse means print in blue. So everything from this print statement onwards will be printed in blue until we reach this control code. And this says print in green. So these characters here will be printed in green. That's followed by another print in blue instruction, so that the rest of the line will be printed in blue. So this is the part I wanted in green. On each line where I've got characters from that shape, I've put a print green instruction, and then immediately afterwards I've got a print blue instruction. If I didn't have those print blue instructions, then the whole of the bottom half of my maze would have been printed in green. Note, of course, that the alignment on the right-hand side has been ruined by the insertion of these extra characters. But don't worry about it, because although when we list the program, these 3 lines seem to be longer than the others, when we actually run the program and print this out, these color control codes will not take up any space on the screen. If you haven't copied a computer program from one of our videotapes onto your computer before now, then this is the procedure you should follow. You need to connect the headphone socket or the line out socket from your videotape player to the microphone socket or the line in socket of an ordinary cassette recorder. While you play the videotape, record onto an ordinary cassette in your cassette recorder. You'll then have a copy of the program on this cassette, which you can then put into your Commodore dataset unit and load it in the same way that you would load any other program into your computer. We can use printing using our graphics characters and letters and numbers to put things onto the screen. But for many purposes, and certainly when we're playing games, using a print statement just isn't fast enough, and sometimes it isn't flexible enough. So if we want things to appear on the screen more quickly, we've got to use another technique of making them appear. That technique is going to involve us understanding a little bit about how the information in the computer's memory is displayed on the screen. So we'll start with a diagram of part of the computer's memory. If you would imagine that this grid represents some of the bytes in storage in your Commodore's memory, then they're used for many different purposes. But we want to look at the bytes that are used for the screen memory. Now you have 25 rows on your screen, and every row contains 40 characters. That gives you a total of 1,000 characters. And into each byte of storage, you can put a character yourself, and that character will be shown on the screen, as long as you put the character into the right piece of memory. Now, on a Commodore 64, the screen memory, as it's called, goes from the byte whose address is 1024, that's this first one, up to 2023, that's all the way down to the bottom. And they're numbered, 1024, 1025, 40 of them across the top row, and then 40 on the next row, and 40 on the next row. So if we want to make a character appear somewhere on our screen, we can address the screen memory directly and put the character we want into that piece of memory. Let's suppose we want to put a value into that character on the screen. Well, as long as we know the address of the very first character on the screen, we can calculate the address of this one we want to use. Now I've put it as row 3, column 5. And it's simpler if we count our columns starting from 0 and our rows starting from 0. So row 3 means 0, 1, 2, 3, and column 5, 0, 1, 2, 3, 4, 5. So let's calculate the address of the piece of memory that will show that character on the screen. Here's the calculation that we need to do. We start at 1024, which is this very first character, the top left one. We add 5, which is the column number. Adding 5 takes us 5 places across to the right. So that brings us here, in the right column, but not yet in the right row. Now, because we have 40 characters in each row, to get from one row to the next, we have to add 40 to the address. So this very first character is 1024. The first character on the next row is 1064. The first character on the next row is 1104. So we find out how many rows we need to come down and multiply that by 40. And that's why we have 40 multiplied by 3, row 3. To come down the screen that much, we have to multiply by 40. And so the answer to our calculation is 1149. So if we put a value into 1149, we'll be putting a value into the byte that shows this position on the screen. So using this calculation, we're able to work out the location in memory, the actual address, where any character position on the screen is going to be. And we can put into there whatever character we like. And if you look in your Commodore user guide for the Commodore 64, you'll find that there's a list in one of the appendices of all the different numbers that you can put into the screen memory to get all the different characters displayed. But there's one problem, and that problem is that although we've specified the character to be shown at a particular point, we haven't said anything about its color. In fact, we have to set up its color separately. Not only do we have to put the character into memory, but we also have to put the character's color into a different place in memory. I'll show you. We have what's called color memory. It's the same sort of principle as the screen memory we looked at a moment ago, but instead of each byte of storage containing a character to be shown on the screen, The color memory contains information about the color of that character. Now your color memory is at the other end of your Commodore 64's memory, from 55,000 to 56,000. As before, the very first byte is 55,296, and the very last one for the bottom right-hand side of the screen is 56,295. So into these cells in memory, we put a number which indicates the color that's to be used. 0 would indicate black, 1 white, 2 red, and so on for all the 16 different colors that the Commodore 64 is able to show on the screen. And we do the same sort of calculation to decide on the address of a piece of color memory for a particular screen character. Let's take this character again and work out what the address not of its screen memory is, but of its color memory. Row 3, column 5. So we do the same calculation as we did last time, but this time we use the address of the start of color memory instead of the address of the start of screen memory. 55,296, which is that very first character, plus 5 for the column number, plus 3 times 40, meaning row 3, taking us down to this particular character, the answer 55,421. You'll recognize this maze shape from the first section of this videotape. We've added 5 characters into it though. And although the maze was produced using print statements and character strings containing graphics characters from the keyboard, these 5 characters have been put onto the screen not by using print statements, but by actually putting the codes for those characters into screen memory and also setting up the color codes for those character positions. Let's look at the coding for that. There's the beginning of the program. The go sub 1000 we had last time, and that draws the maze. We now have another go sub statement, go sub 2000, and I'm using that subroutine, the one that starts at line 2000, to put those symbols onto the screen. So we need to look at the coding starting at line 2000. Here it is, from 2000 to 2999, we have a subroutine. We know it's a subroutine because of that return statement at the end. A comment at the beginning to remind me what this subroutine does. And then a sequence of poke statements, because the poke statement is the one we use to put a particular value into a particular location in storage. Start by looking at the first one. Poke 1066, 83. That says, put the character whose number is 83 into the storage location, the address 1066. So after we've executed that poke statement, if we were to look in storage location 1066, we'd find the value 83. It holds the character whose number is 83. And that's what each of these poke statements is doing, putting one number into each of these addresses in storage. And if you look at these addresses, you'll see that they're in pairs. The first one of the pair is within screen memory, and the second one of the pair is in color memory. And if you were to do your calculations, you discover that each of these pairs corresponds to one character shown on the screen. That's its character, that's its color. That's a different character, but that's the color for that character. So I've used this sequence of 10 poke statements to display these 5 characters and set their colors to these 5 values. Character codes you'll find in your user guide, and also the color codes you'll find in your user guide. So you don't need to try to remember them from the videotape. You can look them up when you go back and work with your computer. It's a bit of a bind though, however, starting to do all these calculations from scratch every time. To work out the start of screen memory, the start of color memory, to work out how many rows down, how many columns across, and then to do the calculation that gives you the addresses in storage. We've got a computer, so why don't we use that to do the calculations? And that's what I've done in the next step in this program. I've written a subroutine that will do that poking for us. Here's the coding for it. It's only a very short routine, line 10,000 to 10,030. And there are only 2 working statements in that subroutine. They're both pokes. The first one is going to poke a character into screen memory. The second one will poke a character into color memory. Now there are 4 variables used here: X%, Y%, C%, and D%. If a variable name has a percent sign on the end, it means it's an integer. No decimal places. And all the numbers we're using for our addresses in the memory, or for our color numbers or character numbers, are integers, so I've used these throughout this little routine. Into X%, we need to put the column number, how far across the screen we want the character to be. And in Y%, the row number, how far down from the top of the screen we'd like the character to be. So this first statement takes 1024, adds X%, and then adds 40 times Y%. So it'll calculate the address in screen memory of the character at X%, Y%. Similarly, the second one starts at the address of color memory and does the same calculation. So it will work out the address in color memory corresponding to a particular character, X%, Y%. C% is a number I've used for the code of the character. So that will be put into screen memory. And D% I've used for the color number for the character, and that will go into the color memory. Having written these calculations once in a little subroutine, it means that from any different place in our program where we need to position a character on the screen, we can use a goSub statement, passing control to line 10,000, and as long as we've put values in X%, Y%, C%, and D%, this routine will do the work for us. To show you how to use this subroutine, I've written a couple of references to it somewhere else in my program. They're between lines 3000 and 3999. If I list those lines, you'll see how it works. Line 3010, 3030 both contain statements goSub 10,000. Before each goSub, I put a value in X%, a value in Y%, a value in C%, and a value in D%. That says in column 10, row 12, I'd like a character whose number is 102 in color 8. This one says in column 12, row 14, character 102 again, but this time I'd like it in color number 7. So all we need to do is put the values into those 4 variables and goSub 10,000. Put a different set of values into the variables, goSub 10,000 again, and each of those would cause a certain character in a certain color in a certain position on the screen. Let's see what happens when we run the program, including those statements. As you can see, 2 new characters have appeared on the screen. That little chessboard type shape is character number 102, which you'll find in your user guide. As you can see, it's been printed in 2 different positions on the screen using 2 different colors as a result of those 2 separate calls to my little poking subroutine. Before I leave the subject of subroutines and go-sub statements, let me cover one point that you may have noticed yourself in looking at my coding, which is that I used numbers starting 1,000 apart for each of my different subroutines. 1,000, 2,000, 3,000, 10,000. Now this isn't essential, but it's quite a good habit to get into, because it does allow you to keep each separate subroutine well separated from all the other subroutines in your program. And it's also easier to remember where each one begins and where each one ends. As a matter of personal preference, I like to put my return statement on a line number ending 999. So a go-sub statement might call a subroutine at line 3000, and the return statement would be at 3999. That's personal preference, but as you write more and more programs, you'll start to build up what I hope are good programming habits. Now we'll copy that program onto the soundtrack of your video cassette at this point. When we come back after that break, we'll look at moving characters around on the screen under the control of you at the keyboard. There are 2 things that you'll notice about this screen that are different to the one before. We have a little purple ball here, which is flashing on and off. And up in the top right-hand corner of the screen, there's a set of numbers ticking away every second. We'll come back to those in a moment. But let's ask ourselves, why is this ball flashing? The answer is, it's waiting for us to move it. If I hold down one of the keys, it moves. If I hold a different key, it moves in a different direction. By using keys on the keyboard, I can control the movement of this ball. Notice it won't go past the walls. If I try and drive it straight at a wall, it stops. So, we've got a way of moving a character on the screen using keys from the keyboard. And also a way of finding out when it's going to meet something that isn't empty space, and therefore not allowing it to move any further. Well, let's look at the subroutine I've added to this program to allow us to have this ball moving around. Here's my subroutine at line 4000 to line 4999. And it's quite complicated coding, so as well as going through it on this videotape, I would suggest you do copy it into your own computer and have a look at it in detail. The Z, the X, the slash symbol, and the semicolon are in fact the 4 keys that I use to move my ball around the screen. The way this subroutine works is that I take one character from the keyboard. I look to see which of those 4 it is, and if it is one of those 4, I remember which it is by deciding how much I've got to move and in what direction. Having done that, I look to see if there's a blank space in that direction. If there is a blank space, I move my ball to the new place. If there isn't a blank space, then I don't do anything but go around and wait for another key. That's the principle of it. Let's look at it in detail. First, let's see what variables are important. I'm using X% and Y% to remember what position my ball is in on the screen. X% to remember what column it's in, and Y% to remember what row it's in. When I move, I want to use dx% and dy% to remember how much I'm going to move and in which direction. So if I use a Z key means move left. So then I would set dx% to -1, meaning my X position has to move left, has to decrease by 1. Similarly, a slash key means I want to move down. So my dy value is 1, meaning I want to come to the next row down. I start by making sure that both dx% and dy% are 0. And then I use a get statement to get a variable $k. Now the get is unlike the input statement that you've seen before, because it only accepts one character. You don't have to press the return key. And also, if there isn't a character ready, if you haven't typed a character, it won't wait. It'll just carry on. So, having set dx% and dy% to 0, I get a character if one was typed. If it was a Z, an X, a slash, or a semicolon, then I can make the appropriate adjustment to dx or dy, meaning I want it to move up, right, down, or left. Having done that, each of these lines goes to line 4100. That's here. Now the next thing I want to do is discover if I'm trying to move into a space or if I'm trying to move into part of the maze. I've written a new subroutine to do that, and that's at line 11,000. And that does really the opposite of a poke. It has a look in character memory to see what character is there. I've used px% and py% to inquire about a particular character. X% plus dx% tells me the X position I'm trying to move to. Y% plus dy% tells me the Y position I'm trying to move to. Take those two values and I put them into the variables px% and py%. And then I use the subroutine at line 11,000. So we should look at that to see how that works. It's a very short subroutine. In fact, really, there's only one line of coding in it. It's putting a value into the variable pc%. And I've used pc to indicate the peaked character. This function, peak, is the opposite of poke. Instead of putting a value into a memory location, it has a look to see what's there. Now you'll recognize this calculation as the one we've been using for the poke. If I'm interested in position px% py%, then that calculation tells me the address in screen memory of the byte in which I'm interested. Peak gives me back a number, and that number tells me what value is in screen memory at that location. That number is put into my variable PC%. And the important value that we're going to be looking out for is the value 32, because if that address gives me back a value of 32, 32 is a space. So it means that at px%, py%, there is a space, and so I can move into that space. Here's that movement subroutine again. Let's look to see what happens after we use the subroutine at 11,000. The first thing we do is say if PC% is equal to 32. We ask the question, are we trying to move into a space? If we are, then we go to line 4,200. That's down here. Because it means that there's a space we can move into, and so we can move our ball from one character position to the next. If the answer to this question is no, it's not 32, that means that there's something in the way. There's something in that character position which isn't a space. So we come to this line, line 4120, and that uses another subroutine. That's one that I hope you're going to write in a little while. Having used that subroutine, we then return, saying we can't do any more movement. We've tried to move into a space that's occupied. So let's look down at line 4200 to see what we do if there was a space. PC% equals 81. Right? Character number 81 is that little ball we're using. So that's us. That's the character we're moving around. PC% equals 81. Go sub 10,000. Go sub 10,000 is the poke routine, like 11,000 was the peak routine. The subroutine at 10,000 uses the same variables as the one at 11,000, px% and py%, to show the x position and the y position. So we set the character to be put in as character number 81, and we poke it into the new position. Now if that's all we did, we'd have the ball in the starting position, and we'd have a new ball beside it, the position we've moved to. The other thing we must do is rub out the old ball. And that's what we do in the next line. Remember I said that when we use the subroutine at 11,000, we're looking for a value of 32, because 32 indicates a space. Well, now we're going to rub out the ball in its old position by poking a space into that character. PC% equals 32. We're going to poke a space character. Where it's going is in x% and y%. That's the old position of the ball. So I make px% equal to x% and py% equal to y%. My poke character is a space, so now when I go sub 10,000, I've put a space where my ball was. Now my ball has moved to a new position. So the last thing I need to do in this subroutine is to update my x% and my y% to show that I've moved it. Remember, dx% and dy% show which direction I've moved in. Has x% gone up by 1 or down by 1? Has y% gone up by 1 or down by 1? This last line here, 4220, uses x%, its old value, and its change to calculate a new value for x%. Similarly, the old value for y% and the change to calculate a new value for y%. So after we've been all the way through this subroutine, we've checked to see what key was pressed. We've set a change in the X position or a change in the Y position, depending on which key it was. We've had a look to see if there was a space ready for us to move into. If there was, we moved our ball to the new position. We rubbed out the old position by putting a space in there, and we've changed X% and Y% to show that the ball's moved to a new position. Now, using BASIC, you're not going to get the sort of speed that you'd expect in a machine language program that you'd bought, but you can still get some quite interesting effects. And we've only shown you one very simple example of using the keyboard to move a character around the screen. You can obviously change the keys yourself, change the maze, change almost anything you like if it's your own program. However, there are a couple of other things that we really need to look at in this program before we move on and tackle another subject. The first of those is the fact that I've made the keyboard repeat automatically. And normally when you press down a letter, you just get one of those letters. You don't get a whole row of them. But for the purpose of this game, I've said to the Commodore 64, when I hold down a key, be it a letter or a number or any other key, then repeat it automatically. And I did that with a special poke instruction, which I'll show you now. In fact, because this poke instruction is part of the initial setup of the whole program, I've put it in a separate subroutine with all the other things I need to do right at the beginning of the program. There it is, poke 650, 128. And you'll find that particular poke in your user manual so that you'll be able to look it up and check it. If you remember, each of these has a function that only needs to be performed once at the beginning of the program. This sets the screen color, the background color, to gray. This sets the starting position for our colored ball, and this prints it on the screen once right at the beginning. So all these things have to be done once and once only at the beginning of the program. If I show you the listing of the first few lines of the program, you'll see how the logic has been set up. I list up to line 999. You'll see that the first thing I do now is call the subroutine at line 9000, and that's the one that sets things up. 1000 draws the maze. 2000 puts those four symbols around the maze. 4000 is the subroutine that moves the ball. Line 60 says go to line 40. So in fact, as soon as we get here, we'll jump back to here, and we'll go round and round. This would allow us to move the ball as many times as we want. This line 50 has the job of keeping track of the time. It's a print statement. It prints home, that's to the top left of the screen. It then moves across to the top right and prints this variable, TI $. That's not one of our own variables. That's a string of characters that the Commodore 64 keeps up to date by itself, and it shows us the current time. As we run the program, we'll see that printing this each time we go round and round this set of statements gives us an up-to-date copy of the time in the top right-hand corner. There's also that subroutine at line 12,000 that I said you were going to write for yourselves. Well, that one is called each time we bump into a wall. So it would seem to make sense to have some sound at that point. Well, we'll take a break at this point, record that program onto the soundtrack of this video cassette, and after the break, I'll show you how to make sounds using your Commodore 64. first sight, the sound facilities on the Commodore 64 might seem a little daunting, but in fact the machine is a very powerful and very sophisticated sound synthesizer. So the sooner you get the hang of what information it requires to make a sound and how you can modify that sound once it's started going, then the sooner you're going to be able to put interesting sound into your programs, use it to compose tunes, and give you sound effects to your games. Now, I've got a small program here which is really just an aid to using the sound facilities, because it allows you fairly easy access to each of the individual aspects of the sound that you can control. So if we start by looking at the program, we'll see what information we need to set up in order to start a sound going. I've used an array, V, and I've set V1 to 54,272, V2 to 54,279, and V3 to 54,286. Now the reason for this is that there are three separate voices, if you like, three separate instruments within the computer, and they're controlled by values you put into storage. The first voice, values starting at this address, the second voice at this address, and the third voice at this address. Now the various values you need to control the different sounds I've listed here as variable names. The voice number, so you have to say which of your three voices you want to make the sound. You have to specify the frequency, and you have to specify that in two parts, the low part and the high part. That's how high or low the note is. And you'll find that there's a table of these in your user manual. These next four stand for attack, that's how quickly the noise gets loud. Decay, that's the speed at which it sinks away. Sustain, and that's the volume level it stays at until it's finally released. So these four numbers here, the attack speed, the decay, sustain volume, and the release speed, all control the way the note sounds. Whether it comes up quickly, comes up slowly, dies away quickly, dies away slowly. Also in your manual, you'll see that there are various waveforms. I've got waveform number 2 here, and you'll hear what that sounds like in a moment. I've set up two little subroutines at 1000 and 1100. And this one will start a note going, and this one will stop it. So you can experiment by changing these different values, listen to the note, and then stop it when you want to try another one. Let's try our first note with these settings. Now here's the subroutine that sets that noise going. And you can see it consists of a series of pokes. I've used the voice address, and VO is the first voice, so all these sounds will come from the first voice only. Frequency low, frequency high. Pulse low, pulse high, which we'll leave on one side. Attack, decay, sustain, release, and the waveform. And if you look at these expressions to see how they're put together, you'll see how we have to put these values into a sequence of 7 consecutive bytes belonging to that particular voice. Now the way I've written this program, you can change any of these very simply and listen to the result. This 1 here and this 0 here are very significant. In the 5th byte of the information for this voice, that's 4 away from the beginning. Although we have to put 16 times the waveform, that's the shape of the sound, into it, we also have to add 1. And that 1 is the on part. That switches the voice on. Here I've got a separate little subroutine, and all that does is to put 0 into the same address, and that switches it off. So this sequence of pokes sets up all the values necessary for the sound and switches the sound on. This one switches it off again. Let's listen to a range of sounds that this program can make. all we have time for on this videotape. We hope you've enjoyed this introduction to Commodore 64 and its BASIC, and I hope that you'll go ahead and write many, many of your own programs. After this, we've recorded the music program and also an expanded version of the maze game program we've been working with during this videotape. Enjoy yourselves.